Hello everyone, and I hope you enjoyed my last video on the Heisenberg uncertainty principle. This question is on the center of mass. Now it's been taken from the SQA 2025 question 19 of the Advanced Higher Mathematics of Mechanics produced by the SQA. And basically we're given a lamina and we're asked to find the center of mass. So what is meant by the center of mass of something? Well, here I've got a ruler, and it's the same thickness throughout, and if I hold it up by the center, you can see it's perfectly balanced. In other words, I have located its center of mass. Now, if I put a small mass on either side, and the small masses are equal in magnitude regarding the mass, again, it'll be perfectly balanced due to symmetry. However, in this question, we need to use a formula for a center of mass, which means we need to use a coordinate system. And the coordinate system is simply the XY plane. Now, our lamina will extend the XY plane, so we're working with both the X coordinates and the Y coordinates. So let's see how we proceed with that. So how do we develop this concept that leads to a solution of this question? So we'll ask for coordinates. So the very first thing we have to do is draw a coordinate system. The XY coordinate system, or the XY plane. And then just focus on the X plane, the X coordinate to begin with, assuming that each separation is 1 centimeter, just to keep it simple. We have a 1 kilogram mass at position X is equal to 2 centimeters, and a 1 kilogram mass at the coordinate X is equal to 16 centimeters. Therefore, the two masses are 14 centimeters apart. What's the coordinate of the center of mass? Well, it's going to be X is equal to 9. Probably work that out yourself. What if the numbers aren't as simple as that though? What do we do there? Well, we use a formula. To find the coordinate, find the X coordinate of the center of mass, and this formula also works for the Y coordinates as well, but they do for the X coordinate. Find the X coordinate of the center of mass, that's equal to m1 times x1 plus m2 times x2 plus m3 times x3, all over the total mass, m1 plus m2 plus m3. Where m1 x1 is the mass m1 at position x1. m2 x2 is the mass m2 at position x2, and so on. Now, if we now use this formula to do a very simple question, you can see it gets 9 centimeters as we would expect. But suppose now the mass at position x2 becomes 2 kilograms, and we use the formula again. Now we get an answer for a center of mass coordinate, X coordinate, to be closer to the larger mass, as you would expect, because the center of mass is the average position of all the masses. And that's always going to be closer to the heavier one. Use different masses yourself and you'll see that. So now, what if we have a non-zero Y coordinate on our hand? Suppose the mass at position x2 is not 3, it's not 16 0, it's 16 something else. For example, in this example here, what is the center of mass of those two? What's the coordinates? So you're going to have a non-zero X coordinate, you're going to have a non-zero Y coordinate. Well, that's easy. Just use the formula to find the X coordinate and use the formula to find the Y coordinate. And you actually see the answer as you would expect, right in the middle. Now, suppose my masses are on the vertices of a triangle. How do we find the center of mass of that shape? Well, it's very easy. You just use the formula for X and Y for 3 pairs of coordinates. Shouldn't be difficult to do that. Notice the center of mass is closer to the two masses at the bottom, as you would expect that, because that's the average position of all the masses, and there's more masses towards the bottom than at the top. So we would expect that. But notice here, there's a wee simplification we can make. All the masses are equal. All the masses are equal. Our formula reduces to coordinates divided by the number of coordinates. And that's simply the average of the coordinates. Now that's quite significant here, because if I take my masses away and just look at the coordinates, the average of the coordinates will be in the exact same place. So if I put a solid triangle there of uniform density, the center of mass of the solid triangle will be in the exact same place as the average of the coordinates. And that's how we work out the center of mass of a triangle or any other shape with points, well-defined points in a coordinate system. We can simply find the center of mass of that using the average of the coordinates. We can't do that for a semicircle, of course, another part of our problem, but we've got a formula for that worked out using integral calculus. And the formula to find the y-coordinate of a semicircle is 4/3 of r over pi, where r is the radius of our semicircle. And that's all we need to know to solve this problem. There's one other thing we should know, that if we do have a solid body, and we know its mass, and we know its center of mass, then what we can assume is, for this problem or for other problems, that all of the mass is concentrated at its center of mass, and we can proceed from there. If we have, for example, a solid extended body, and we wish to do a free body diagram, we always draw the weight vector through the center of mass. So now to our problem then. We're asked to find the center of mass of this lamina that consists of two shapes, the triangle and the semicircle. The first thing we need to do is find the center of mass of those two shapes individually. And we know the center of mass of a lamina, we've been the line joining it to. To find the center of mass of the triangle, average of the coordinates, as we explained earlier. To find the y-coordinate of the center of mass of the semicircle, we use the formula 4/3 times r over pi. Remember, the x-coordinate will be 3 centimeters due to symmetry. Once we've found the center of masses of these two things, we need to find the center of mass for the whole shape. For that, we use the formula. But if you look at the formula very closely, it says we need to know what the mass of the triangle is and the mass of the semicircle is, and that's true. However, the mass of this shape will be is equal to the density times the area times its thickness. That will give you its mass. But the density and the thickness are constant throughout. Therefore, if we put these two values into our formula, multiplied by the area, no matter what they are, they will cancel out, leaving us with the area. So it's sufficient to know the area of these two shapes. And the area of the triangle, that's just a half the length times the base. And the area of the semicircle, that's a half pi r squared. And when we do that, we get our coordinates for our lamina. And as you can see, they're right on the line joining the two center of masses of our two separate shapes. Now, the center of mass of our lamina is 2.34, 7.47. I should have got the shape here. And that means the center of mass is round about here. So if I put my finger round about here, now remember, this isn't of uniform density, and the dimensions might not be exactly 9 and 6. But I should get a center of mass round about here. So if I put this on my finger round about here, I should balance the shape. So we'll do that. You see, yeah, balanced. And that means my finger has located the center of mass, which for a perfect lamina of this shape and size will be 2.34, 7.47. Here we have it. Last question. We are told the lamina is suspended from point 8. My fingers here supporting it just now. And we're asked to find the angle the downward vertical makes with the line AB. And I'm holding line AB just now. If I let it go, then what happens? The downward vertical goes directly through the center of mass, and we're asked to work out this angle here. Let's see how we do that.